Hello everyone, welcome to the second installment of Beginner Data Science Guide. In this episode, we're going to see another competition. After seeing Titanic last week, we're going to see house prices. This problem is to predict sale prices of houses and taking into consideration a lot more parameters than we have commonly know about how to buy a house, more than like the number of bedrooms, presence of a garage, and a lot more. Here we're going to focus, as Kaggle says, in feature engineering and in advanced regression techniques. We're going to see random forests, gradient boosting, lasso regression, and finally stacking models in order to pull them into our advantages to obtain better results. So let's start, and as always, we'll do our inputs. Here, the basic ones that are always involved in data science projects, and of course, sklearn. Here, I would appeal to the norm and the skew instead, as most special and box squad 1p as well, to make more context with the libraries from Python. We're gonna oppose the input that we already have here on data. You can see training test as always. And we can see that we have a lot of features in this training set because that's the idea present in this problem. There are a lot of features that we most normally don't see when we are beginning our journey in data science. Here we can see that we have an extensive number of features, mainly 81 here, of course, including sale price, but we're going to eliminate the ID because it does not matter for the prediction. So we're going to be left with 79 features, meaning that 80 is only the sale price. But for starters, we have to understand outliers. For those who don't understand what outliers are, those are points or observations that are not well correlated. That means that in the final prediction of our model, they wouldn't make much sense being there. Let's give an example. For here, we're going to plot this graph presenting the sale price and the ground living area. We can see here there are two examples that give us that are two houses with big ground living areas, but somehow, some way, they are really inexpensive. We know that commonly that does not happen, so we might remove them. Proceed here to remove them, and we must take care because outlier removal is not always safe. There are a lot more outliers probably here, but we cannot mess with them that much because they will impact our final results in a meaningful way. So for now, let's stop in this operation because of these two outrageous points. Next, we have to understand what we want with our model, what are our predictions towards to. This is sale price, we're going to analyze it, and we see that it's not normally distributed and with right skew. What does this mean? Well, models prefer to work with normal distributions because it's easier for them, let's say. So we perform a log transformation in this variable that is introduced by the function numpy log1p, and after the appliance of this we can see that it's normally skewed and we have a normally distributed sale price feature set. We can do now feature engineering. Here we have to understand how much missing data we have in the data sets, because if we have missing data we have to transform it into something that we can operate, or if we know that we cannot operate with it, we must remove it. We have all the missing ratios here. Of course more with pool, but that's normal. Let's take this example. Not all houses have pools. So here the presentation of NA would mean that this house has no pool. Um, Here we have the plotting of the percentage of missing data, and we have to see how correlated the data is with sell price with our target variable. Here indicated with our more clear is more correlated with it. It represents one. We can see that there are several parameters that are not going to be well correlated with it. So what are we gonna do here? We're gonna input the missing values. By this we have to see the categorical, the numerical, and understand other ones. For example, for categorical here, we have bool, misc, feature, alley. Most of these are presented NA description, but that only means none. So we're gonna go through for cycle. We're gonna substitute NA with none. Here we're gonna do the same with water frontage. We say that house property will have a similar area to the other houses in its neighborhood, so we're gonna do the median with a lambda function to be faster. Here with the numerical features, we're gonna substitute it with 0 instead of none. Also for this parameter, the classification RL is by far the most common value. So we're gonna fill the missing values with RL by this function. Also for the functional feature set, this is different than the other categorical ones, because in this data description, NA normally means typical, so we only substitute it with typical, not with none. And for the utilities feature set, we see that all records are all above except for 1 and 2 NA. Since the house with no sewage in the training set, this feature won't help with the predictive modeling because it's only in the training set. So you can just drop it. With this, we're gonna analyze if there are serial missing values, and we see that none. With this, we're gonna transform some numerical features that are really categorical, and we afterwards gonna do label encoding of these categorical features. Here we also choose to add one more feature, as we did in the past example with the Titanic. We're gonna create the total area, total square footage of the house by the combination of these three feature sets, and then we're gonna check the skews in the numerical features. You can see that there are some skew presented, so we're gonna use the boxcon 1p input that we already talked about in the very beginning. To be mentioned is this lambda is 1 is gonna have the same function as log 1p, so we're gonna proceed with lambda equals 0.15, and with this we can create our train and our test. Afterwards we do the modeling of these operations. We're gonna create a cross-validation application followed by the definition of the regression operations that we are gonna impose. The lasso regression, elastic net, kernel ridge regression, gradient boosting, XCV regression, and GBN. For this we do the model scores, and we can see that, for example, with the XCV boost, by the way, these warnings, you just ignore them. It's normal. We can see that's slower. Slower. It's in fact slower, but it's better results. But we're gonna go to stacking models. After obtaining all these values, we can see that if we stack models on top of each other, we can and use different operations of machine learning, can achieve better values. This is a graphic to help you guys understand better what is model stacking. And with this, we're going to create a class with averaging models. This one will be averaging 3 different type of models. This is a more simple stacking of models. It's very common. You can find it in the internet everywhere. And we're gonna average 4 models: the elastic net, gradient boosting, kernel ridge regression, and lasso regression. With this, we can see that we can obtain even better results than the ones up than ones formally presented. But now we can create a meta model. What is this? It's an even more complex engineering model stacking. We're gonna split the total training set into 2 disjoint sets. We're gonna train several base models on the first part. We're gonna test these base models on the second part with a holdout, and use the predictions from the holdout as the inputs and the correct responses as the outputs to train a higher level learner called the meta model. For us, the meta model is gonna be here is the class defined for the stacking of average models for the second example. And here we're gonna average elastic net, kernel ridge regression, and gradient boosting. And we're gonna treat lasso as the meta model. Here we can see that we can achieve even a better result. And with this, we're gonna do an evaluation function with RMSLE. This of course means the mean squared error. And here we're gonna propose the ensembling of stack regressor, XGBoost, and byte GBM, because these are the ones that present the better results. Here we can see that after stacking them, we can obtain this score that is even better. With XGB fitting the train and test. You can see this. And finally, by allowing the combination of these different types of these better results, by giving the importance of 70% to the stack train thread, to 15% to the XGB, and 15% to the LGB model, we can obtain the least possible mean squared error representative of 0.075. After this, you can of course do the summation. You create on the outputs your summation in form of the CSV, and that's it. That's basically the house prices tutorial. Thank you, and hope next week you'll join me back again. Bye bye.